Okay, I've got a 5-minute limit with Jing, so this is going to be really rapid fire. I'm going to skip over most of the stuff that logism implements on its own and try to stick with the details that show my knowledge of this circuit. So bear with me, this is going to be really fast. First, let's talk about the PROM here. The PROM, or Programmable Read-Only Memory, allows me to input hex values in order to output 8 bits, which are then separated into two 4-bit words, the least significant of which are used as a data input, the most significant of which are fed into a decoder. Figuring out what I want to do is just a matter of determining what an opcode consists of, like what bytes are needed to be output in order to perform a specific function, and then translating those into those hex values. Same thing happens with the decoder. We just figure out exactly which of these 8 bytes we want lit up and put those options here in the decoder. So this 4-bit address, this opcode, is then able to select the right function and light up or power the correct wires here. Those wires then power the write enables on my register file and my ALU, as well as the ASCII. They also control addressing on this multiplexer and on the register file itself, and of course on the ALU. In the ALU, it's going to select which of the functions we want to run. In the register file, it's going to select which of these registers we want to write to, and in the multiplexer, it's just going to select which source we're going to use to feed into that register file, either the ALU's output or the data input from the programmable ROM. Okay, I've got several subcircuits to go over here, so let's dive into the register file first. Register file consists of 2 registers as well as a decoder. I did this myself, even though I could have used a logism. We'll just look at that real quick. Functionality is fairly simple. Turn it on and off, and it switches between the 2. So, let's go back up and take a look at a register. Do that. Okay, the register contains 4 1-bit registers, and it takes a 4-bit input, stores them in those registers, and feeds it out as an output. Very simple. And the single-bit register is just a D flip-flop with a multiplexer that enables us to have this enable pin. We can turn on and off whether or not this is going to accept any new input. Okay, the big one though is the ALU. Let's look inside there. This has 4 functions that it can run: the AND, or add, or, and exclusive or function. Each of these functions is performed on these 2 inputs and is fed into a multiplexer. This function select determines which of these outputs is going to be fed into the accumulator, which is just 4 D flip-flops, which is going to store that data for us so that we can handle it on the next cycle. This is the hardware subtract, which we'll get into in a minute. For now, we're going to take a look at the sub-functions here. The add is just going to use 4 full adders, which look like this. This is just a standard full adder as we went over in class, so I won't go into detail. Okay, now we'll go into the OR real quick. The OR is 4 ORs, the AND is 4 ANDs, and the XOR is 4 XORs. Each of them is just pitting the 0 against the 0, 1 against the 1. You get the X. Okay, now we get to a bit of the fun part. I'm going to go ahead and run this circuit. We're going to see what happens. I'm going to run it on a tick frequency of 32 Hertz so that we'll see it rather quickly. Alright, so here we're writing ASCII values. Okay, pause the simulation here. The way we write an ASCII value is just to set 0 and 1 to the total, to the binary value of that ASCII digit, and then we feed it into the ASCII. Now we're going to see it run several arithmetic functions. So 3 plus 4, 7, 3 times 9, or 3 times 3 is 9, 4 minus 3 is 1, 4 minus 3 is 1 again, and each of those is done with the ALU. 3 plus 4 is just run to the adder, 3 times 3 is just adding 3 times, and 4 minus 3 is where it starts to get a little interesting. Okay, we're already going into the second video here, so I apologize for the amount of time. I'm trying to keep it as short as I can. Anyway, 4 minus 3 in the software is a fairly simple thing to do. First I feed in a 3 and a 15 into these registers, and I XOR them together to get the inversion of 3, bit inversion, and then I add 1 to get the 2's complement version of 3. And then I set 2's complement back in here, and then I set the other one to 4 and add them together to get the final answer, which is 1. So that's the software version. The hardware version does essentially the same, well, actually it does exactly the same thing. It's just done in a single cycle. But it'll feed in that 4 bits here, matches it with a manual 15 and a manual 1, and outputs the correct value over here. So when we put in 2, we're going to get the 2's complement version of 2 out. Same thing with 3, just like this. Oh. Well, we won't do that then. It's a little bit of a logarithm gap there. Anyway, yeah. The only other thing to look at that we haven't taken a look at is this 8 to 7. All that does is takes in the 2 4-bit words and puts out a 7-bit ASCII value instead, and drops one of them because that's what the ASCII display requires. Alright, that about sums it up. Sorry again that I'm over time here, but I condensed as much as I could. Just as an addition, each of these longer strings here was rather simple for me to do. I wrote an extra script in Ruby that allowed me to input a string value and then get actually a hex set out of it. So here, let me pull that up and I'll run that for you. Alright, so here we are in a command window, and then I have this script here, code generator. We're just going to run it, and it asks me to put in something, so I'm going to put in howdy, and it'll output. It gives me a file name, and I'll say howdy. Let's do that. Alright. And here is the output. It actually puts it out in the format that Logism accepts. So we could read this in. In fact, let's go ahead. Okay, we will just open this howdy file and close this window, and we'll go ahead and run it again. And there we go. Howdy. So, simple. It works out pretty good. This is a fun project, and I enjoyed the class. Thank you very much, and hope you have a great day and a Merry Christmas.